주는 몇 센치에 떨래 I wanna keep the bass down low 벌써 내 맘은 주말모 I don't see no open cars, no open bars 나쁘지 않아 온전히 혼자인 row 섬처럼 떠있는 사람들의 맘 어쩌면 오지 않을 듯한 밤 지평선을 걸어가 또 굴러가 우리 다정한 소시점으로 슬프면 자전거를 타자 바람을 두 발 아래 두자 자전거를 타자 두 팔을 자유로 벌리며 나나나 가끔은 굴러가게 둬 자전거 바퀴처럼 자직해 있어 오후의 간식처럼 이 작은 순간을 위해 살아온 것 같아 두 바퀴 위에 선다 사사로운 한낮의 꿈 Feel the roof, smell the truth 멀지 않아 기적은 어떤 얼굴을 해도 지금은 괜찮아 진짜 소중한 건 눈에 보이지 않아 땅에서 바를 때저 새를 닮은 때 숨처럼 떠있기로 해 바람을 따라 춤춰 예우려도 돼 원래 행복한 슬프면 자전거를 타자 바람을 두 발 아래 두자 자전거를 타자 두 팔을
Firstly, we are going to look at the concept of static equilibrium balancing. In static equilibrium balancing, we are going to define a couple of words that are static and equilibrium. Static means that it's not moving, and equilibrium means the force is equilibrium and that everything is balanced. Now, for rigid bodies, all objects, all forces have to be balanced in all directions. That includes x, y, and z directions. In this hydraulic marble travel project, we apply the knowledge of static balancing on a marble, but note that this marble is not a rotating mass, but a rigid body. So we use the approach of balancing concept to make the system being controlled by forces applied by 4 different corners in order to make sure the marble to move or being stationary at a certain places. In terms of an equation, it's the sum of the forces has to be equal to 0. What we don't want to forget is the board itself probably has a mass, and if we think of our center of gravity concept, we are going to have that right there at the center of the board. If we observe the system, when I put a marble over on one side, if it would tend to make the board want to tip down on the side, but if I put another mass on the other side, it could balance out so that it stays balanced. Obviously, there's a force due to the mass pushing down over the syringe on one side and a force due to the mass pushing down over syringe of the other side. Plus, if we apply the same exact forces at each syringe, the board will statically balance and resulting the marble from not moving on the board. However, if we apply different forces on 4 syringes, we can observe that the marble keeps on moving along the maze path, hence the reason why it can find its way from the starting point of the maze until the finishing line. So here, in static equilibrium balancing, we can see the marble can be both balanced and unbalanced state depending on the position of marble on the board and force applied at each syringe corner.
The second concept that we apply is fluid mechanics. From the definition, fluid mechanics is action the study of fluids either in motion or at rest. In this project, we apply hydraulic system as the idea behind of hydraulic system is that force is applied to one point and is transmitted to a second point using an incompressible fluid. The hydraulic marble travel consists of 8 strings and we connect them with tube that fill with food coloring. We fill the strings with 4 different types of food coloring to know which strings control which part of the corner of cardboard. We need to take note that if there is an air bubble in the system, then the force applied to the first string get used compressing the air in the bubble rather than moving the second strings, which has a big effect on the efficiency of the system. So we need to make sure that there is no air bubble in the strings. From the video, all the movement of marble is controlled by 8 fill strings. As we push the plunger on a syringe, the fluid is forced into a second syringe, extending its plunger and lifting the cardboard. This process illustrates that the hydraulic supply acts like providing the energy for pushing and pulling the fluid. When we push on the plunger of the movable syringe, the cardboard rises. When we pull on the plunger, the cardboard descends. Pushing on the plunger applies pressure on the water in the movable syringe. This relates with Pascal law, since the fluid is confined and incompressible. Pascal law tells us that the pressure is transmitted undiminished to all parts of the fluid and to the walls of its container. Since the plunger of the fluid syringe at the other end of the tube forms part of the container for the fluid and is the only part for the container that can expand, the pressure causes the plunger in the fluid syringe to move. And the last point, the force is equal to pressure multiplied by area. Since the pressure on both plungers is the same and the areas of both plungers are identical, then the force on both plungers is the same.